All systems are nominal. Initialize Genesis sequence.
Hello, everyone. Thanks for coming. My name is Stuart Marks. I work at Oracle in the Java Platform Group on core libraries. And the best contact for me is on Mastodon these days. And I'm here to talk about Java's Fraught relationship with cyclic object graphs. Now, we do work for Oracle, and so that means there has to be a safe harbor statement. The material contained in this presentation is 100% pure, artisanal, organic, natural intelligence. No stochastic parrots were harmed in the making of this presentation. All right, so cycles. This is kind of a general topic. It's not actually new technology. All of these issues have been floating around for a very long time. But I haven't seen, the reason I decided to give this talk is I haven't seen anybody give a survey of all of these kinds of issues. And so what I've done here is I've chosen 5 examples of where cycles can occur among various different constructs in the Java platform. I'm going to touch briefly on modules and the class hierarchy. Then I'll talk about static class initialization, which is somewhat obscure topic, but it does tend to figure in large systems. And then we'll talk about the object graph, which is the network of actual object instances in the JVM. There's some issues with equals, hash code, and toString, which I will cover. And then finally, I will spend rather too much time talking about serialization and deserialization, and what happens when you try to do those with object graphs that have cycles in them. Okay, so I used a few terms a moment ago, so I want to go very briefly over some graph theory. I'm not going to talk about the theory very much, but I am just going to go over some terminology. So in a graph in mathematics or computer science consists of nodes and edges. And so I'm representing nodes with circles, and edges are the connections between the circles. And the edges can have, they can be unidirectional or bidirectional or directional, and that's indicated by the arrowheads. And so mostly we will be dealing with what are called directed graphs. And this should be pretty familiar, because if you have 2 objects in Java, A might have a reference to B, but that does not mean that B has a reference to A. In fact, it is usually not the case. So object references in Java are directed edges in the object graph. Okay, so there are different topologies of graphs that can occur. So you can have a tree, which has a root, and each node might have 0 or more children, and every node has 0 or 1 parent. And then in the middle, there's what's called a DAG, a directed acyclic graph. And so that's kind of like a tree, except there are some variations here, which I've highlighted in orange. So a node can share children with other nodes, or conversely, if you look at it the other way, a child can have more than 1 parent. And then on the right, there's an example of a cyclic graph. And so if you look at the arrows, the orange arrows in the cyclic graph, you can find a path through a cyclic graph that eventually returns to a node you have seen already. And that's not true of the others. And so this is what the issue of cycles is all about, is dealing with these. So there are a lot of algorithms, a lot of tasks in practical programming that involve graph traversal. Even though we don't necessarily call it that, that's what's there. And so the primary task of traversing a graph is visiting each node, we hope exactly once, walking along the edges. And so with a tree, you can just visit each child, and then if you do that recursively, everything just works. And so your tree traversal is fairly well understood, I think. Now, if you try to apply that to a DAG, an issue comes up. Since parents can share children, you have to start thinking about what it means, because you might end up visiting the same node twice. So you might have to deal with that somehow. Now, if you have a cyclic graph, you can get into real trouble, because if you just start following links, you will literally, almost, end up going around in circles, and you will never terminate. And so there are that's the big concern with traversing a cyclic graph. And so there's a lot of graph theory out there and traversal algorithms, but in practical usage, mostly what we do is we do use recursive algorithms, and then if we want to deal with if we want to avoid cycles, getting into trouble with cycles, or visiting a node more than once, we will sometimes use a side table to keep track of what nodes that we have visited already. Okay, so a brief note on modules. So modules can form a graph. You can see two module declarations here. Each module is a node, and the requires clause forms a dependency between modules, which is an edge. So we have mod.A, module mod.A requires mod.B, and mod.B requires mod.A. So it's actually a little bit tricky to assemble modules that have these dependencies, but you can do it using separate compilation. And so once you have these modules, if you attempt to load them into the JVM, at module initialization time, you will get this error shown below. So the module the boot layer initialization code will actually do a graph traversal and detect a cycle. And in this case, it decides that it's an error. So you get the error below. And actually, it's quite nice. It tells you where the cycle is. It says resolution exception, cycle detected, mod B depends on mod A, depends on mod B. So that's pretty explicit, but it's also pretty well a solved problem. So that's all I'm going to say about modules. Class hierarchy is actually sort of similar. We have classes, and classes have dependencies on other classes expressed through the extends and implements clause. We talk about class hierarchy. That's not really true. The class is actually the class graph is actually a DAG because you can have multiple implement classes listed in the implements clause. And so when you load a class into the JVM, it will do some graph topology checking on the class that you just loaded to make sure that it conforms to its constraints. And so here I have a very simple example of actually I'm getting ahead of myself here. We're still at compile time. You can actually very easily write some source code that expresses a cyclic class dependency. So class A extends B, so there's a dependency there, and class B extends A. So of course, this, we think about inheritance, and it doesn't make any sense. And so if you try to compile it, you get this error message from the compiler. It says cyclic inheritance involving A. Okay. And now, through separate compilation, you can actually arrange to have two actual class files that have those dependencies. And if you attempt to load them into the JVM does its graph traversal checking, and you will get a runtime exception, which is class circularity error. And so it's a little less explicit here, but this is basically the same error. Introducing A into the classes in the JVM involves a circularity, which is illegal. And so the JVM checks for that and rejects loading that class. OK, so I think modules and classes in at least the inheritance hierarchy, or at least the inheritance graph, are, I think, pretty well solved. And they don't really tend to cause problems for people. What I think does cause problems in practice is class initialization. And so I am going to spend a little bit more time on this. So we talked about loading classes in. So after a class is loaded, before it's used, the JVM needs to initialize it. And that involves calling out to Java code, because class initialization runs static blocks and it runs initializer expressions for static fields. And so this initialization occurs immediately prior to the first time the class is used. And so that's fine. But what's interesting is that you can write code in static blocks for one class that involve other classes. Or you can also do that in field initializers. You can depend on other classes in your static initializers. Well, that in turn might require that second class also to be initialized. And so that initialization occurs while the first class is being initialized. So you can say, there's a dependency here of one class initialization on another. And, as you might be able to guess, this class initialization dependency, these relationships, form a graph. Now, what happens if that graph has cycles in it? OK, so the language has some very strict rules. You can read the JLS about this, but I'll try to summarize it here. When something needs to use a class, that class is first initialized. During initialization, if that initialization requires another class, then that class also needs to be initialized. And you keep following that chain. Eventually, if your class initialization dependency graph has a cycle in it, you're going to encounter a class that is already in the act of being initialized. And so what happens here? So you can imagine a variety of things. You can imagine throwing an exception or crashing or something like that. But what happens is that the JVM looks at this and says, OK, sorry, you have a cycle here. We're trying to initialize classes, and we've come back around the circle to a class that is in the midst of being initialized. But it depends on these other classes, and we're coming back around to the beginning. Sorry, some code is going to see some class that is in a partially initialized state. And here's where the problem is. All right, so, and I'm going to attempt to demonstrate that for you. All right. OK, hope everybody can read that well. All right, so I have a fairly simple program here. All right, so I have basically there's a outer container class, doesn't do anything, it just holds the code. But we have three classes here, A, B, and C. So A has a field I, and these are all static, which is important because we're talking about static initialization. Class A has a field I, and its initializer expression depends on B. And class B has a field I that depends on C. And class C has a field whose initializer depends on A. So you can pretty easily see the cycle here. So I have a main program here that just constructs a new instance of A. And so the rule is before the first use, that means that actually, it's very interesting. Class initialization is completely lazy. If you never mention A, then, or if you never mention these classes, then they actually will not get initialized. So you have to do something that causes the class to get initialized. So constructing an instance of a class requires it to be initialized first. So before the constructor runs, the class is initialized. So let's run this and see what happens. OK, so A's I field is 3, B is 2, and C is 1. How did that happen? So we started off by initializing A. And so note, the right-hand side of the initializer for the expression I is evaluated. I has not been assigned yet. A's I field has not been assigned yet. So we're in the middle of evaluating the right-hand side. And the JVM notices that class B needs to be resolved. And it's not initialized, so then it needs to be initialized. So we've suspended the initialization of A, and it starts initializing B. And so B has, how come I can't highlight anything here? There we go. OK, so B has an initializer here that depends on C. And then C, now here's the situation I was talking about a moment ago. So C now depends on A. And so A is in the midst of being initialized. But note that its field I has not yet been assigned to anything. And so what happens to a field if it hasn't been assigned yet? Well, when the JVM has a rule that every field has a default value, which is 0, false, or null. OK, so in this case, I is 0. So A.I is 0, and we add 1. And so I is 2. So C's I is 2. B gets that and adds 1. Sorry, 0 plus 1 is 1. Sorry, do the arithmetic here. OK, and then B adds another 1, and then A adds another 1. So that's why we get 3, 2, 1. Now, let's just change this line of code here to reference a different class in the cycle. OK, so now we get different values. And I'm not going to go through it all, but I think you can see, depending on where you start in the cycle, will expose a different class to being partially initialized, to be partially initialized when something is read from it. So in this case, it's well, yeah. So it's A that. Oh, all right, never mind. But you can see that instead of 3, 2, 1, the values of these fields are 1, 3, and 2, and that's because we changed which class started the whole chain of initialization. All right, so that was a really simple example, but as code gets more complicated, then you can start to run into deeper troubles. OK, so here we have another example. We have classes A and B. And so A has a string field that's initialized to foobar, and then it has a len field that is initialized to the length of B's string str field. And so B has something similar, but notice the fields are declared in the opposite order. Another rule in the language is that static initialization is performed left to right, which really means from top to bottom. And so fields are initialized in order. So here, so you can see again that A and B have a dependency among them that is expressed at static initialization time. So let's see what happens when we run that. Okay, so we construct A. So it initializes string foobar and then B's string length. So that causes B to be initialized. That uses A's string field and gets its length. So that's 6. And then it assigns string to XYZCY, which is 5. And that, in turn, is used here. So that's why we get 5 for the length in A and 6 for the length in B. Now, let's see what happens if we construct a different class and start something in a different position in the cycle. Ouch! What happened here was, just because the way things happened, so B started to be initialized, and it says, oh, I want to initialize class A and get its length. Actually, what is this? Yeah, OK. So it initializes, so we're here, and it initializes class A. And so class A static initialization is performed. We assign foobar to string. And then we have a reference back to B, and we want to look at B's string field. OK, so remember, we suspended initialization of B right here, and that means string is unassigned. Even though we tried to initialize it, as early as we can, it's actually still null at this point, because we have this class initialization circularity. So A is now exposed to B in a partially initialized state. And so here, actually, it's very nice. We have one of these nice new error messages. It says, we get a null pointer exception because static $b.string is null. And so I think this is starting to illustrate when your systems get complicated, if you do too much stuff in static initializers, you can easily run into this by accident. And so how many of you, I want a show of hands here, how many of you have been working on a large system and you made an apparently innocuous change, and then the system just totally blew up in a completely unexpected way? OK, about half the people. And maybe, I'm not sure, I'm not good at crowd sizes, but a couple hundred people here. So yeah, a lot of hands raised. So I don't know for sure, but this might be the reason for that. And so it's a problem, and you have to be aware of it and figure out how to cope with it. All right, I think that's, oh, actually, and I do have a way to cope with it. OK, so we have some tooling that provides some diagnostic information for this. And so there's, actually, it's harder to read. But this line here, you can, on the Java command line, you can say xlog class resolve equals trace. And that will trace class resolution. And so if you run, I ran this previously, and this is the log output from this. And it's quite voluminous. But what it does is it gives you the information you need to know. And it would be nice to have some tooling that does this. You can actually construct the class initialization dependency graph from the information in here. So if you have a class resolve log line, there are 3 arguments here. So this one is explicit. These are the usual things when it tells you the reason why a class is being resolved. And explicit means that it was explicitly named in source code. There are other reasons like reflection and stuff. So, this is a fairly common one. But in this format, the first word on the log line is the class that is generating the resolution request. So that's from. And then the second one is to, which is the class that needs to be resolved. And it's actually very nice. It gives you the source code line here where that occurs. And so actually, so if you have this problem and it's weird, it's a lot of work, but you can actually go, there are thousands of lines in this file. So you can pick out and find out where your class initialization circularity is and figure out what the classes are involved in the cycle. And the difficulty is, this only tells you, the exception gets thrown from one particular class, and that tells you where you can start looking, but there's nothing as yet that tells you which other classes are involved in the cycle. let's see, where's the, just wanted to mention one more thing. We did, I was talking with several folks yesterday, we did have this idea where, gee, it would be nice, since this is an odd situation, it's not necessarily an exception, but it might be nice to have something like a JFR event that tells you what's going on. Actually, I'm going to go out on a limb here and I say, if we add this JFR event, I bet when you bring up the JDK, it's going to result in class circularity issues that just happen to be innocuous. Because I personally have had this experience in working in the JDK where I added something and then it completely blew up. And it's like, oh, it's a static initialization circularity. I don't want to deal with this now. So I just backed out the change and did something else. And I think most of you have had that experience. So yes, this is a real issue. OK, back to the presentation. OK, so now let's talk about cycles among object instances. So if you create a bunch of object instances, they all inherit equals. Well, they all have methods on them. Equals, hash code, and toString are the most common ones. There are a few others I'm not going to talk about. But those are the most common ones and the most significant ones for most Java programmers. And if you override these, then they don't have to be recursive, but they effectively often are, because many classes represent values, and a class holds data in its fields. And so if you want to compare such a class, or such an object for equality with another instance of the same class, you typically get the fields and call equals on each of the field values. And it's kind of the same with hash code. You get the hash codes of all the fields, and then hash those values together, and that's this class's, or that's this object's hash code. And toString is a little bit different. It often calls toString on all of the fields of the class, and then concatenates them, or formats them, or something like that. So effectively, this is a recursive algorithm, even though, well, you can, even though it's calling the method on different objects. If you have a cycle, then you can easily see that it's recursive. OK, so collections, of course, I work on the collections framework, so collections have to come into the presentation somewhere. For collections, the equals, hash code, and toString methods are all fairly well defined. In particular, and they're all, I'm not going to go through all the details here, but they all have the same flavor. It's just that the equality or hash code of a collection is not based on its fields, but rather the elements contained in the collection. So if you have a set, what's the hash code of the whole set? Well, you take each element, get the hash code of every element of the set, and add them all up. And if you look at the set specification, it says that's the hash code of a set. So essentially, that's kind of the same thing. That effectively gives you a recursive algorithm. So I'll just do a brief demonstration here of that in action. So here we have a pretty simple program. It creates two hash sets, set1 and set2, and adds each one to the other. So you have hash sets that point to each other. What happens if you print out the hash code? I don't even bother printing it out, because as you know, it's not going to work. All right, so we get this gigantic stack trace here, which is a stack overflow error. So basically, hash code just went back and forth between the two objects, saying, what's your hash code? Oh, I need your hash code. What's your hash code? Right? And then it overflowed the stack. So that's a pretty obvious thing. But if you do have cycles among collections, you can run into that. But there's an interesting question here, which is, I mean, it's like, maybe this is a bug. Maybe we should try to fix it or something. But actually, something like a hash code is ill-defined in the presence of cycles. So you could try to find a fixed point value that works, but there's nothing in the hash code spec that says, oh, OK, if you have a cycle and you can cut off graph traversal and then return some value. I don't think that would work, because it would probably depend on, if you started at a different point in the cycle, you might have different objects having different hash codes at different times, which is probably a bad idea. So if you try to figure out what the definition of something like hash code or equals is, you could probably cook up some definition of equals. in the presence of cycles. I don't want to try to do it here. But in practice, nobody's going to write the code that deals with a circular graph inside of equals and hash code. I think Throwable's toString does, or maybe there's something in Throwable that actually has to do this. But for the most part, they don't do this. And so if you call equals and hash code on a cyclic object graph, you get a stack overflow error. And if you call toString, you might get a choice of stack overflow error or out of memory error, because it's going to start allocating strings and concatenate them, and eventually it's going to run out of memory, maybe before it runs out of stack space. It might run out of heap memory before it runs out of stack space. So anyway, maybe we should have a hash code. Maybe we should tell people to have hash code algorithms that detect this. And we probably don't want to do this. The easiest way to do this is to create an identity hash map, and every time you visit an object, then store it in the hash map, and then that way you can detect that you're in cycle. So we could put that into like the utility methods or in the collections algorithms. But we generally don't want to, because the point of hashing is to be fast. And so you don't want to create a bunch of memory and initialize an identity hash map just to keep track of where you visited and then throw it away. It's going to slow down every hash code in the system, and we want hash codes to be fast. So we just kind of live with this. OK, now everybody's favorite topic, serialization. So I am talking about classic Java serialization here, which was introduced in 1.1, as Brian said in the keynote. So this is one of the problems we have been dealing with for quite a number of years. And this is interesting because what's happened is that there have been a number of bugs built up, these weird errors that occurred with serialization. And kind of what prompted this talk was a customer said, what's going on here? What should we do about this? And so it's like, well, in the spirit of customer service, I decided to do a full investigation and uncovered a whole pile of bug reports over the years where these inexplicable errors occurred in serialization. And they were, it's actually far too, my analysis was far too detailed to present here, but there are like 4 or 5 different flavors of problems that can occur with cycles and serialization. And I'm only going to go over 1 or 2 of them here, depending on how you count. But in the act of doing here, I don't think, I mean, part of this is driving a decision of, well, there are these bugs in the bug database. What are we going to do about them? And the answer is, I do not think we can fix them. OK, so first of all, if you read the serialization documentation, it says that it handles cycles, and it kind of does. If you have a bunch of objects that have direct object references to each other, what serialization does, it does a graph traversal, and it does what I said a moment ago. It creates an identity hash map, and as it serializes objects, it throws them into the identity hash map, which it calls the object table. And that way it can detect cycles, and it handles that. And so what it does is when you're serializing objects and you encounter an object that you've seen before, instead of serializing again, it says, oh, I've seen this before. I will include a backref into the entry in the object table. And then it can just move forward. And so it linearizes a cyclic object graph into a linear stream. And so that actually works. And deserializing those works as well. So basically, when you're deserializing things, deserialization builds up the object that's deserialized into an object table. And then if it encounters a backref, it says, oh, I know, I've seen that object before. It just plugs in the object reference and continues going. So that actually works. The problem is that only works if you have a direct object reference to another object in the object graph. If you have a relationship between objects that involves the object's state, then we start getting exposed to that same old problem of partial initialization, or somebody in the cycle is going to be exposed to a partially initialized state of another object, and that's where all the problems are. OK, so I talked about this a moment ago, the serialization procedure. So basically, it does a recursive descent through the object graph. for every class, it writes the object descriptor, serializes the fields, and then this is pretty key here. If it's seen an object, it looks up every object it encounters in the object table. If it's seen it before, it serializes a backgraph. If it hasn't seen it before, it just proceeds to serialize it. And then at a certain point, it will complete serialization of the entire object graph. And the side effect of that will be the production of a serialized byte stream. OK, so that works. Now, the deserialization procedure is kind of that in reverse. So what happens is it reads an object descriptor from the field, and based on the descriptor, it instantiates the class, but it doesn't call the constructor. It does this special magic thing where it instantiates the class empty. So all fields have default values, which is 0, null, and false. And then, now it's still in the process of deserializing this object. The first step is just creating the empty instance. And then what it does is it proceeds to read the field data and deserialize it. Crucially, when it's deserializing the field data for this object, it keeps it off to the side. It doesn't stuff it into the fields one by one. It keeps it all off to the side. There's a bunch of history there, which I don't have time to go into, but if anybody is interested in that, this has changed over time, and that made things even more complicated. But the simplest thing is to say, OK, it's deserializing fields for an object, and it stores that up in a buffer. It stores those objects in a buffer off to the side until it's all complete. And then there's the thing about backgraphs. If you run into an object, if you run into a backgraph in the serialized stream, it pulls it out of the object table and then stores it in there. But all the stuff is kept off to the side. And then when we've deserialized all of the field data successfully for this object, then we assign the fields. And then that completes the serialization, the deserialization of this object. OK, so now I'm going to demonstrate that. All right, so this is a bit involved, so I'm going to walk you through the code here. All right, so I create a simple class called a box, which just has a single field, which is a set. And it's a set of box. And of course, it's serializable. And its hash code is the same as the set's hash code. And so for a variety of reasons, I have not overridden equals here, but it's not actually relevant to the example. And then toString, I had to override toString here because, well, because it doesn't work if I don't. But basically, what I want to do is just print out the identity hash code of this object. Yes. The reason is that the default implementation of hash code actually calls the hash code method. And we want to avoid that because of the previous demonstration. We'd easily get into a Stack Overflow error. OK, so printing out one of the boxes just prints out box with identity hash code. OK, there's a little print utility that prints a box and a set of box. And now I'm going to use a hash set here, and so hash set has a toString method that prints the contents. It prints all its elements. It calls toString on all its elements and puts that in brackets. So we'll see that in a moment. And then there's a little utility method here, which all it does is takes any object, serializes it into a byte array output stream, takes the byte array, deserializes it, and returns that object. So there's a bunch of code here, but there's really nothing fundamentally interesting going on here. So now I have a couple test methods, which I'll get to in a moment. And so main is where the circularity sets up. We create a box, and we create a set, which is initially empty. And then we put the set into the box, and we put the box into the set. So there's our circularity. It's just that we have two different classes in play here. So now I'm going to run the test set method. So what that does is it starts the serialization with the set, and then, so it calls serialize, deserialize here. So it serializes the set and then deserializes it, and we get a different instance of a set. And then we get the box out of this set by just getting the first element of the iterator, and then we print them out. So what happens here? OK, so that actually worked. Maybe. All right, so we have a box with some identity hash code, and we also have and it has a set, and the set's contents are the same box with that same identity hash code. Okay, so that kind of worked. Or did it? So if you have a box, this set looks like it contains this box. I mean, that's what the printout says. So let's ask the set if it contains the box. Okay, Stack Overflow error. So why is that? So contains, the first thing it does is you hand it an argument. It does some type checking. Well, actually, no, it doesn't do any type checking. Basically, it has to look it up. So the first thing it does is calls hash code on its argument, because it's going to use the hash code to look up in its internal table to see if it has that element. And so the hash code of box depends on set, and then set says, oh, I need to compute my hash code, I need the hash code of my contents. And so I call hash code on the box that contains me, and here we get our circularity and Stack Overflow again. So even though it looks like it worked, it doesn't really work. But this is kind of a fundamental problem with this anyway. Actually, the same thing would occur if you called set.contains on the original box in the set. So that's actually not related to serialization. What is related to serialization is if you start the serialization at a different point in the object graph. So test box does kind of the same thing as test set. It's just that it starts the serialization at the box object. So we take the box, we serialize and deserialize it, and we get a second box. And then we print out the box, and we print out the set that it contains. And then we also ask whether it can actually, well, let's see if that works. Actually, I'm going to comment this out because I think that that's not germane to this. All right, so that that has the danger of Stack Overflow error. But anyway, so if we run this, we get an exception, but we don't get the Stack Overflow error. We get a null pointer exception. Cannot invoke set.hashcode because this .set is null. All right, so okay, so this is a little puzzle. So I have some attempts to visualize this here. So this is the object graph that I set up in the code. So we have a hash set, and there's just this internal simplified representation of its table where element 0 points to a box, and the box has a set field which points back to the hash set. Okay, so we serialize it. Okay, what happens here? So we start with a hash set, and the serial stream contains the descriptor of the hash set, and then the descriptor of the box, and then the box points back to the hash set. So instead of actually serializing hash set again, we have a backgraph to the hash set instance. All right, so now what happens if we deserialize that? Okay, so the first thing in the serialized stream is the hash set's descriptor, followed by its serial data. So upon reading the descriptor, we create our empty hash set. And so it's all empty, zeros and nulls. And then we start to read the serialized data that the hash set contains. Okay, so again, like I said earlier, this is kept off to the side. We have a box, but we haven't stored the reference to the box in the hash set yet. Okay, so the box is created, and it is initially empty, so its set field is null. Now we proceed to read the field data for box, and what happens is its field gets filled in from a backgraph that points back to the original hash set. Okay, now we've finished reading the hash set's field data, and so that reference from the side data structure is now filled into the hash set's data. Okay, there's actually a little more complicated stuff going on underneath, but this is essentially what happens. So in the one case, we've actually successfully restored this cyclic object graph if we started at hash set. Okay, there we are. Now, what happens if we start serializing at box? So it's kind of the same, it's just that things are in a different order. The first thing in the stream is the descriptor of the box, followed by its field data. Then the descriptor, which is the first thing in that, is the descriptor of the hash set. And then the hash set has its data, which is a backgraph to the box. So let's see what happens when we try to deserialize that. Okay. So the first thing here, notice we're starting over with the box at this point. So we've created an empty box, and its set field is null. in a side data structure, we create a hash set and store its reference in the side data structure, and we create an empty hash set here. The next thing is hash set gets a back ref to the box. Okay, so we have that, and so we can point it at our already existing box instance. And what hash set does, the first thing it does is it can't store it inside of itself. It doesn't store it into a field. What it has to do is it has to call hash code on the object that's being stored into it in order to figure out where to store it. But the box's set field is null. So even though we have the element, it's off in a side data structure, and box is totally uninitialized at this point. So that's why we get a null pointer exception. When hash set calls hash code, it asks box for its hash code, and box's hash code gets a null pointer exception because it doesn't have its set yet. But it won't because the exception is thrown and deserialization stops. So that's why starting at a different point in the cycle gives you radically different behavior. All right, so that does not work. All right, so let me go back and show a slightly different example here. Okay, so this is the issue here. We have a circular data structure, but box introduces, or it exacerbates the circularity because its hash code refers to the hash code of its set. So let's try to fix this in a variation here and say, okay, yeah, that's a problem here. So let's just set the hash, let's set a hash field to be 1 and then just return that field. All the rest of the code is the same except for a couple things down here. In these little test routines, I print out whether we believe the set contains the box. And I think that's it. So we'll just run this. Okay, so that worked in scare quotes, right? So in both cases, we got a box that has a set, and the set contains that box. Okay, but in the first case, the set believes that it contains the box. But in the second case, the set cannot find the box inside of itself. So why did that happen? Okay, so I could do another fancy build, but I ran out of time to do that. But I think you can see that it's the same story again. We have a cycle, and we're constructing objects, and somebody somewhere in the chain is going to be exposed to another object that has not been initialized. And it turns out here, you might think, oh, this is a constant or something, isn't it? Shouldn't the field always be 1? Well, no. During deserialization, when the box instance is first created, it's empty, which means that all its values are 0, null, and false. And then deserialization proceeds, and the hash set is asked to store this box into the hash set, and its hash code at this point is 0 because this field has not yet been initialized. So it sticks it into bucket 0. And then later on, when deserialization finishes, it reads in the field values for box, and now box believes that its hash code is 1. And so if you ask it whether it contains this box, it says, what's your hash code? 1. I'm going to look in bucket 1. Oh, there's nothing there. Sorry, I don't contain you. So this is arguably worse because your code apparently worked, but now your data structure is corrupted. So this is a problem. Okay, what are we going to do about this? Nothing. All right. So the problem here is that too much of this depends on the application. And it's one of these things like, if you write code that has an infinite loop, or if you write multi-threaded code that has a deadlock, it's not like the JDK can fix those problems for you. So creating a cyclic object graph, unless you're exceedingly careful, you will get yourself into trouble. And there's not very much that the JDK can do to fix it. We can probably add some tooling and stuff to aid in diagnosis of these issues, but this is not something that we can fix. Okay, so I have several pages of summary and advice here. So static initialization is a pretty common problem. I think I asked for the show of hands previously. It seems we don't know that it's static initialization cycles that cause this, but I've seen this occur in enough complicated systems that I believe this is a common pathology out there. I think a common anti-pattern I've seen is doing too much work in a static initializer. And if you do too much work in a static initializer, it means that you're referencing other classes. And if those other classes are also doing too much work, there's probably a cycle sitting in there somewhere. So maybe there's problems that are lurking in such code bases. So I would recommend removing work from your static initializers and replacing it with an explicit post-initialization pass, or doing something like dependency injection or something like that. I suspect those frameworks have ways to control order of things so that you make sure that things are fully initialized before in the right order. I showed that xlog command line that can print out your class resolution logs. If you really get into trouble, I think the information is all here. It will be difficult to go through in painstaking detail, but you can construct the serialization. Sorry, you can construct the static initialization dependency graph from this information. And maybe this is just an idea we had literally yesterday. Maybe we can add a JFR event to flag things like this. Okay, overall, avoid cycles with objects if you can. And there are ways for doing that. You can refactor your object model. Instead of having direct object references, the problem with direct object references is you can store them in arrays, but arrays are very inconvenient, so people want to store them in collections. And it's very easy to say, oh, okay, let's throw a bunch of these into a set or a map or something. And that's where you get into trouble, because set and map depend on the object state in order to find and store and retrieve objects. And state initialization is the problem here. So if you can factor out the relationships among objects in the graph from the objects themselves, then that will give you a benefit. Of course, it means that you have to add another data structure over here, and you have to give every object a name or an ID or something, and then you record the relationships between them using their names instead of direct object references. Because, of course, any problem in computer science can be solved by adding another layer of indirection. But that will work if you get yourself into trouble with this. Another thing is, maybe you could consider not overriding equals in hash code. Because if you don't override them, the default implementations of these use object identity. And maybe that's what you actually want. And so if you're storing nodes in a graph, if you have two nodes that have the same edges to the same neighbors, it's not clear to me those are actually equal, because you might have a graph that has two distinct nodes that have the same edges in them. So maybe equals is not the right thing to use here, or like value equality. So, but mainly this involves thinking hard about the semantics that you want. Another variation of this is to, instead of doing the classic thing of equals in hash code, processing all the fields, reduce it to a subset of the fields. Is that the right thing or the wrong thing to do? I think it's often the wrong thing to do, because if you have two objects that say they're equal yet have different data in some other fields, maybe there's a semantic issue there. But you have to think hard about what you're doing. But sometimes this might be a solution. Also, if you're serializing such an object graph, then maybe those things you're not including in equals and hash code should be declared transient, so they do not appear in the serialized stream. Serialization collections, again, are the problem, because there are probably other things out there that might use equals and hash code, but set and map are the most common occurrence of this, where you can get yourself into trouble. If you really want to serialize a graph that has cycles, you can invoke some of this magic machinery in serialization. You can do custom serialization with read object and write object. Turn them into arrays, and then there's a register validation step that can post-process that stuff after serialization is done, so that you can restore those collections. And then again, declare some fields transient. Okay, and finally, so while we're on the subject of serialization, Victor Klong and Brian Getz will be talking about futures for serialization, and my belief is they have decided to outlaw cycles of serialization. Woohoo! So when they tell you that, this is the reason why. And that is today at 4:40. Thank you. See you on Mastodon.